Today we're going to take a look at section 8.2, which is integration by parts. And to kind of give you some sense of where this sort of comes from, I want you to think about what you know about the derivative of u times v. U times v, if you take the derivative of a product, what do you have to do? What do you do when you take the derivative of a product? Yeah, it becomes the sum, right? It's got two pieces, and there's a summation sign between them and an addition sign between them. And we take the derivative of each of the pieces individually, with the other piece left stationary, right? Exactly like it was before. So it looked something like this. The product rule for u times v said that we have u v prime plus v u prime. This would be a version of this. And if we integrated, that is if we put an integral sign on all three of those pieces, so let me actually show you what I mean on the one that's there. So if we did this, then we would have this version of it right here. So on the left-hand side, you know, the integral of the derivative would cancel each other out. Those are inverse operations. And then on the right-hand side, we would write v prime as dv, and we would write the u prime as du. And if we rewrite this in a different order, that is, if we solve for the integral of u dv, we have the integration by parts formula. So integration by parts comes from the product rule, okay? Totally coming from the product rule for derivatives. And this is really the only version of it that you need to remember. You don't have to remember, as far as I'm concerned, you know, the derivation of it, how it came about. But just, you should know that it came from the product rule. So we are going to be using this form for finding antiderivatives. And typically speaking, what will happen when you're using this is it will look like you're trying to do something where there's a product. Okay? There are a few cases where that doesn't look like that. It doesn't look like there's a product, but as you know, there's always a product because your function is always multiplied by dx at the end, right? And that's a product. So there really is always a product there, but most of the time we're going to actually see something that looks far more noticeably like, oh my goodness, this is a product, okay? So some guidelines for choosing what u and dv are. dv should be the most complicated part that fits the integrand of a basic integration rule. That is, it's the most complicated thing that you know how to take the antiderivative of in the problem. And then u is the part that will become simpler if you take a derivative. Okay, so for example, can you think of functions that become simpler when you take derivatives of them? There's a whole class of functions that when you take the derivatives, they become easier to simpler to work with. Constants, yes, I agree. Constants become better because they become zero, right? What else becomes nicer? Does anybody remember, can you help Abby out with what the name of those kinds of functions are? Powers, And that's a very general rule. I was thinking about polynomials, but powers actually, they don't always become easier because like if you have fractional exponents and stuff, they kind of look ugly. But polynomials do, right? I mean, like if you take something that comes from x to the fifth and it becomes x to the fourth and you take the derivative, it's x cubed, you're stepping down in terms of the power each time. It's a simpler function to work with. Yeah, can you think of a function that definitely does not really change, become easier, helpful at all when you take derivatives? Trig functions, that would be the one. That's the one I was thinking of too. You take the derivative of sine and you get cosine. You take the derivative again and you get negative sine. And it just keeps going round and round, right? Cyclic, I mean, because those are cyclic functions. All right, so you have some kind of idea now of thinking through what might be helpful to let u be and what might be helpful to let the dv be, okay? So let's actually do an example. On this one, I have one piece of this that's actually not either of the two types of functions we worked with. I have natural log of x. But think about natural log of x. Do you know how to do its derivative or its antiderivative? Its derivative. Yeah. You actually do not have a form for the antiderivative of natural log yet. We will talk about how that works later because there is a form. It's in tables in your book, or you can do it actually with integration by parts. But you don't know how to do an antiderivative specifically for that. So that actually helps. So here's how I set it up all the time. And I, as you guys know, because I've said it before, I'm a very visual person. So I set up things visually the same all the time because the pattern to me is helpful. So here's the way that I always set this up. I put a U here and a DU, just like I was doing U substitution. And then over here beside it, I'm going to put a V and a DV. Again, it looks like the U substitution sort of format. Now, what I'm going to fill in is I'm going to fill in this diagonal. All right? The form over here says I need a U and a DV, and that's the green diagonal that I just highlighted. Okay? So I'm filling in that diagonal with pieces from this function, and every piece here has to go in one of those two locations. It either has to be written next to U or it has to be written next to DV. Okay? Can't leave anything out. So what we want is we want to put something inside of U that gets easier. So you might be like, well, I really want to put an x cubed in there, and so do I. But the problem is that natural log of x, it absolutely can't go inside of dv, right? Because you don't have an integral form for the natural log of x. So the u part on this one has to be the natural log of x. Which means, although I would normally like to put the x cubed in there, I'm going to be stuck putting it down here. I promise it'll all be okay in the end, okay? So bear with me. Where did... yes, and natural log of x is kind of the only one that's like that. I mean, really. There is one other function that when you take its derivative doesn't get any easier or harder either way if you do the antiderivative or the derivative, and that's e to the x. So that's actually another one where you can kind of just fill it in anywhere you want because it doesn't really help you or hurt you anywhere. Okay? All right. Yeah. It's not the derivative. It's going to be a derivative. We're going to do an antiderivative here in a minute. Yeah. There's one more piece I need to put somewhere, though. The dx. Where's the dx have to go? In the dv. It's got to go in the dv because it's part of a derivative. So really remember, when we put this notation right here, what we're really doing in shorthand is doing dv dx equals x cubed, and we're just moving the dx to the other side. That's really what it is. We just don't write it out like that each time. So the dx has to go on the right-hand side of the dv formula. Okay, so we have filled in everything we need to fill in from the original problem. Everyone agreed? Everything has a place. On the left-hand side where we have the u, just like with u substitution, we're going to take a derivative. So what is the derivative of the natural log of x? 1 over x. Don't leave me hanging. What are we missing? dx. Thank you. 1 over x dx. When I fill in the right-hand side, I'm given dv, and I need to find v. So how do I do that? I integrate, right? I take an antiderivative. So what's the antiderivative of x cubed? Okay, so it would be 1/4, and it's x to the 4th, and we leave the plus c off for now because we'll involve it later anyway. So we don't really need to worry with it at the moment. Okay, everybody good so far? This right here will make or break you. If you can fill all the details in, you're going to be fine for the rest of the problem. If you get messed up at this part of the problem, the rest of the problem is just not going to work out at all, okay? All right, so what we're going to do next is we're going to take this problem and we're going to rewrite it with the properties that we had seen over here. The first thing it says that I'm supposed to do is multiply u times v. So in my world of visualization, what I do is I multiply across the top here. Just multiplying the two that are along the top. So I have a, and I'll just multiply them sort of in the order I like to see them in when I'm done, a 1/4 x to the 4th natural log of x. I like the numbers in front and variables before logs and things like that. So this to me looks much cleaner than any other version of this. All right, the next piece over here says that I'm supposed to do then a subtraction sign and then an integral of v du. Okay, so I've got a subtraction sign. I can do that, no problem. And I'm doing the integral, and the integral I'm doing is of the other diagonal. So now I'm doing this diagonal. And I have a 1/4, that's fine. In fact, you might even want, and I kind of like to put the 1/4 in front of the integral sign. I'm a fan of putting the constants in front. What do you notice then with the 1 over x and the x to the 4th? They reduce. Not really cancel, but they do reduce. What do they reduce to, Abby? They reduce to x to the 3rd. And there's still a dx here, of course, right? All right. Now, here's the fun thing. You might be looking at this piece and say, but it's still a product. And you would be right. It is still a product. And you know what's cool about that? Totally fine. Do you notice what it doesn't have in front of it? An integral sign. You don't have to do anything with it. It's done. It's done. But, of course, the other piece is not. So my answer will have, whoops, try that again. My answer will have the 1/4 x to the 4th natural log x. And now I actually need to take the antiderivative of the x cubed. Of course, I've got the negative 1/4 out here in front. What's the antiderivative of x cubed? We've already done it once. Yeah, x to the 4th over 4, 1/4 x to the 4th. And then, as Abby mentioned earlier, we're taking an antiderivative in a general form, right? So we do have a plus c on the end of this. And all that's left to do is to clean up the fact that I've got a 1/4 times 1/4 here. So my final answer ends up being 1/4 x to the 4th natural log of x minus 1 over 16 x to the 4th plus c. I've got like a rainbow on my screen now, don't I? It's a fantastic view. How pretty. All right, what do you think? I think we should try another one. Right? Yep, the integral of u dv is what we're looking for. And it's uv minus the integral of v du. And, I mean, we can worry about, like, the language that I just set it out in. You can memorize the formula if that's what resonates with you, or you can think about it in terms of visuals, which is how I think about it. Any of those work just fine, just whatever matters and makes sense to you. All right, notice on this one. It does, in fact, have that e to the x I just mentioned earlier, right? And the thing we know about e to the x is that e to the x does not get simpler or more complicated as you take derivatives or antiderivatives of it, correct? So while it could go inside of the u or inside of the dv, it's the other piece of information that's in the problem that gives us the indication of where it should go. The other piece is x cubed. So x cubed, will it get easier or harder as you take its derivatives or antiderivatives? Where would it be most useful for it to be? It would be useful for it to be in the u. Why, Abby? Yeah, it gets easier as you take its derivative. So u will be x cubed, which means the dv is what? E to the x dx. Okay, what's the derivative of x cubed? 3x squared dx, good job. And then what's the antiderivative of e to the x dx? Just e to the x. All right, so we're going to multiply across the top. U times v is going to give me x cubed e to the x minus the integral along the other diagonal. So when I multiply along the other diagonal, and I'll show you why here in a second, I'm going to keep my 3 on the inside here. I have 3x squared e to the x dx. What do you notice? It looks a lot like what I started with, doesn't it? It looks like product. I've got 3x squared times e to the x. Products are kind of a no-no, right? They require us to use integration by parts again. This is the second step of integration by parts on this problem. We're going to do another u du, and another v dv. But you're an old hat at it by now. What do you think u is going to be? Yeah, the 3x squared, right? And what will the dv be then? That'll be e to the x. What's du? 6x dx. And what's v? E to the x. Oh, and I left my dx off the dv. Sorry about that. Okay, so the trickiest thing really at this point in a problem like this is keeping track of your negatives as you go. I'm going to be honest, because we're going to get lots of negatives involved. Down here, I'm going to continue the problem. So I've got the x cubed and the e to the x. And I've got a subtraction sign. I'm going to put a bracket here for a moment. I'll simplify by distributing it through in a minute here. But I need another u, v, so that's across the top. So that's 3x e to the x. 3x squared, sorry, e to the x, minus the integral along the opposite diagonal. So the other diagonal right here gives me a 6x and an e to the x and a dx. So before I go too much further, let me go ahead and clean up all my negatives that are going on because they're kind of crazy looking with all the brackets and parentheses. So I have x cubed e to the x minus 3x squared e to the x, and then what? Plus the integral of 6x e to the x dx. And what do you notice? There's another one. Oh my goodness. All right, over here we have another version, or another time to do the integration by parts version. U du and a v dv. It is going to be our last one. You're exactly right. How do you know that, Abby? Yes, because when I take the derivative of the 6x here in a moment, I'm going to get a constant. All right, so the 6x is u. The dv is e to the x dx. Continues to be. All right, what's the derivative of 6x? 6 dx. And the integral, that looks like b dx. I'm going to try that again. 6 dx. That's better. What's the integral of e to the x dx? E to the x. Okay, I think I might should have given myself some more space here on this particular slide. We're getting closer. We have x cubed e to the x minus 3x squared e to the x. All that's from the previous work. And then we're going to do this piece. So across the top, I'm going to get, so this is uv, so this is 6x e to the x, minus the other diagonal, right? It's down here. So minus the integral of 6 e to the x dx. Oh, I think I have enough space to finish this on this slide, actually. That's great. All right, x cubed e to the x, that's nice. Minus 3x squared e to the x, that's also friendly. Plus my 6x e to the x, no problem. Nothing to be done, actually, yet. And now I need the integral of 6 e to the x. That is 6 e to the x. Yes, it is. And then what? Plus c. Now, one of the things that you've done before with polynomials and derivatives and antiderivatives is, solving them by setting them equal to 0 for different reasons and stuff like that. If you were to set this equal to 0, if it didn't have the plus c, of course, on the end, you should notice that it's the e to the x in front of every term would factor out, and you'd be left with a polynomial. This polynomial is x cubed minus 3x squared plus 6x minus 6, right? And you might be able to work with that from there. So just a word of just observation on that problem. All right, any questions on that one? So the answer to this problem shows you the process by which we found it. Shows you that integration by parts can be used multiple times in a problem, right? Yeah, it can. All right, this one is an interesting one because it has an e to the 2x in it, which is much like e to the x. And as we discovered in the last problem, when you have e involved, it just continues to repeat itself over and over again, right? I mean, we've got derivatives and antiderivatives are all going to be e to a power, e to a power. The other thing that makes this problem interesting is the sign value. which we mentioned before, is going to do the same thing. Derivatives and antiderivatives, going to go back and forth between sines and cosines and positives and negatives, right? So you might be looking at this and be thinking, okay, well, there seems to be no end in sight on this problem. I'm just going to take derivatives, antiderivatives, keep going. But this is a very classic type of problem, which is why I want to show you what happens when you have two such functions in a problem. All right? So what we're going to do is we are going to let the u be the e to the 2x. And the reason we are is because when I take the derivative, I'm going to have a chain rule because the 2x in the exponent. That's the only reason that that's helpful. If the sign had been sine of 2x, we would have put sine of 2x as the first piece, okay? Because of the inside function. That's how we're making that decision. The dv then is the sine of x dx. So to start with, I need the derivative of e to the 2x. So what would the derivative of e to the 2x be? 2e to the 2x dx. Yeah. So the derivative of e to the x is e to the x. So e to the 2x, and then the derivative of the 2x is 2. So we have times 2. Yep. All right, so now you have to be real careful when you're working with sines and cosines that you're doing them in the right order, right? We know this is going to be cosine. The question for us has to be, is it positive or is it negative? This one is negative. Good job. Okay, everybody good so far? Got all our pieces in order. Fantastic. All right, so we're going to integrate this using integration by parts. So we're going to multiply across the top. So I have negative. You can put the e first or you can put the cosine first. I'm going to put e first. So negative e to the 2x cosine x. And then I have minus the opposite diagonal. And it's not the color I want. Let's try something different. How about that? This actually will have a negative in it because of the negative cosine. It's going to change this to a positive sign here. And then I have the integral of, and I've got the 2 in here as well. In fact, I'll move the 2 to the front. Yeah, I did that in my notes too, so that's good. So we'll put the 2 in the front. And then I have e to the 2x cosine x dx. And of course, you should look at that and go, that really was completely unhelpful, Dr. Hands. That did not really do me any good. And at face value, you would be right. Okay, you would be right. We're going to repeat the process one more time, and I'm going to show you a cool trick that happens with this problem. And it happens with sines and cosines and these repeating kind of, derivative, antiderivative functions like this more often than not. It doesn't happen super often, but it happens when these things have these features. So we're going to do U substitution again. U, du, v, dv. Did I mess something up?
Isn't it supposed to be cosine after the integration? Because it's supposed to be dv. It's v dv after the integration. Or did I write that?
It is v du at the integration part. Okay, that's right. But definitely want to make sure our notes get in there correct. Okay. We're going to follow the same pattern we did before. If you don't like the 2 in front, you can put the 2. In fact, it might be more helpful to see the 2 inside. If you'd like, we could probably do that just for the sake of clarity. That was an awfully big eraser. Let me try that one more time. That's better. Let me go ahead and put the 2 in here just so it'll be a little bit easier to do our integration without something in front of it. We're going to do the same thing we just did a minute ago. I promise it's going to get better. Okay? Just bear with me. And then the dv would be the cosine of dx, or cosine x dx, excuse me. I'm not, because I chose right here at the beginning to change this positive to a positive so that I didn't have lots of negatives floating around. I don't like lots of negatives. They end up making things more difficult. So, all right, so what's the derivative of 2e to the 2x? It is 4e to the 2x dx. And what's the antiderivative of cosine? Sine. Fabulous. All right, so we're going to take this and we're going to rewrite it down here now. This equals, I still have the negative e to the 2x cosine x from before. And I have the top now, so plus uv. So this is 2e to the 2x sine x, and then minus v du, this diagonal, which is integral of 4 e to the 2x sine x dx. Now, you're looking at this and you're saying, well, I'm right about where I started, and you're so close to the correct thinking that it's scary. I'm going to move my 4 out here in front, and then I want to show you something cool. Oh, that was not what I meant to do. Try that again. Check out this piece and this piece. They're exactly alike. I know one has a 4 in front of it. I'm not worried about that. I'll show you how to deal with that. But the integral pieces are exactly alike. Oh, that was wonderfully done, Evan. Yes, I am. I'm going to think of this as an equation because, believe it or not, it is. We don't really think about them this way along the line. But this is an equation. On the left-hand side, I've got the integral of e to the 2x sine x dx. And on the right-hand side, I've got the integral of e to the x sine x dx, right? I'm going to treat it like a variable. I want to solve for it. So I'm going to add the 4 integral of e to the 2x sine x to both sides. Okay, so when I do that, how many of them are going to be on the left? 5 of them. That's right, Seth. So I've got 5 times the integral of e to the 2x sine x dx. And on the right, I have everything but that, right? I have all those other pieces. I have the negative e to the 2x cosine cosine x plus 2e to the 2x sine x. And of course, the other pieces canceled. That was the whole point. What's my last step? Divide by 5 or multiply by 1/5, either way. So I have the integral now of e to the 2x sine x dx on the left, and each of the pieces on the right are either divided by 5 or multiplied by 1/5. So I have negative 1/5 e to the 2x cosine x plus 2/5 e to the 2x sine x. And there is a plus c on here that we need to make sure it arrives at some point. And this is our answer on the right-hand side to the question that on the left-hand side we manipulated with like a variable. Does it feel like a trick to you? It feels like a trick to me. It feels like we're doing some kind of a trick, like it shouldn't be allowed. But of course, I just told you that it is, so it is. All right. You guys ready for the next one? It's much easier. How's that sound? Sounds good. I've shown you sort of some weird, complicated ones because I want you to see some weird, complicated ones because they can get weird and complicated. But they aren't all, of course, weird and complicated. All right. Yeah, I'm doubting it as well. But you've got it printed out for next time, so it's all okay, right? It's all good. All right, take a look at this one. This one has an x, and it has a square root of x minus 5 dx. Now, the directions in your book were going to say integrate. And they will also say next to them, and the directions on WebAssign, not every problem needs integration by parts. So they're asking you to make the determination on every problem whether you really need integration by parts. And this one you don't. Okay, you do not need integration by parts. It kind of looks like you do because you've got multiplication in it, agreed? But you don't actually need integration by parts. And this is one, it came up earlier for us in the semester, and at the point when it came up, I thought, oh, this is where I expected it to come up, was in this lesson. And it does come up again. While this doesn't need integration by parts, it does use U-substitution, but in a kind of funny way. Okay? So we don't like the fact that there's a square root with addition and subtraction underneath it. So we're going to change it so it doesn't have addition and subtraction underneath it. And we do that with U-substitution. So we're going to let U be the part that's underneath the radical that's got the addition and subtraction in it. And as you do that, of course, you notice that the du is not very interesting. What is it? Yeah, it's just dx. And you might be thinking, okay, now I've got a u underneath the radical. I can eliminate the dx on the outside, but there's still this sort of forlorn x out here all by him, little alone himself. You can't have an x and a u in the problem at the same time, right? It's not okay. But what you do have is you do have a relationship that's between x and u that you can change to be solved for x. What does x equal? U plus 5. And you might be thinking, yeah, but wasn't our whole goal to get rid of the subtraction? And the answer is, well, sort of. It was to get rid of the subtraction because it was under the radical. That's the problem. So we don't have any problem with addition and subtraction if it's outside of a radical. So the x gets replaced by u plus 5, and the square root stays square root, but has a u underneath it and a du at the end. And the reason that this is friendly is because I can distribute this now. You can distribute if the addition's on the outside of the radical. You can't do it if it's underneath the radical. So this becomes u times u to the 1/2, or times, so this is u, and this is u to the 1/2 right here. We'll add those together in a second. And then you have a 5u to the 1/2, and the du, of course, at the end. So what is u times u to the 1/2? U to the 3/2. So I have u to the 3/2 plus 5u to the 1/2 du, and we're working with something we know how to do. It just kind of looked funny at the beginning. So what's the antiderivative of u to the 3/2? Right, 2/5 u to the 5/2. And what's the antiderivative of 5u to the 1/2? Okay, so the u to the 1/2 becomes u to the 3/2, and we do times 2/3. So we have 5, I'll write it out as 5 times 2/3. It is, of course, the 10/3 that you mentioned. And then I have a plus c, right? So I have 2/5. All right, that 2 is a square root, right? And u, of course, is x minus 5, wasn't it? Yeah, x minus 5 to the 5th. Plus, and now I have 10/3. I have a square root, and I have x minus 5, whoops, to the 3rd, plus my c. I'm fine if you want to leave it there. WebAssign might make you pull out the fact that this is to the 5th when it's a square root. It's quite possible that they will, and if they do, what it means is you're going to have an x minus 5 squared out here, and then a square root of x minus 5. And on the second piece, you're going to have a 10/3, and you're going to have an x minus 5 and a square root of x minus 5 plus a c. I don't know if it's going to make you do that or not, but it might. Okay, does everybody understand how I got from the place where I said you could stop to the next place? If you don't, now's the time to ask. Not sure? All right, so the reason is because of this 5/2. 5 divided by 2 would be 2.5. So the 2 is what came out, and then the 1/2 is what stayed under. That's the easiest way to see it since we looked at it from the perspective of the exponents. Yes, it is easier to look at if you leave it in the u form and then do the bringing out. Absolutely. Yeah, but it's because of that exponent 5/2 and that exponent 3/2 is because it's 2.5, 1.5. Okay. All right, we have one more problem. At least we can finish this lesson today, even if we can't move on into 8.3. Find the definite integral. And I put this one in here on purpose because, not because of the definite integral part, that's really not a big deal. The big deal is that you notice this doesn't really look like multiplication, does it? And I told you that there is one case that kind of just really doesn't. And it's the case where we've got the natural log part of it. Okay? So, yeah, we've got this natural log involved, and it is U substitution because of that. So let me show you how that works. U du, v dv. U is the natural log because that's the part we don't know how to take the antiderivative of. So we're going to take the derivative of it instead. And although it's not very interesting, dv is dx. All right, so the derivative of natural log is what? 1 over whatever's inside of it. And in this case, that would be 1 over 4 plus x squared. Times 2x. Yes, ma'am. Okay? Yeah, dx. I'm out of space. Let me move my little pieces over here. But yes, I need a dx. Okay, then, we need to know the integral, or the antiderivative of dx. It is x. It would be plus c, but it is x. So this is understood to be a number 1. 1 times dx, so we get x as an antiderivative of that piece. Okie dokie. I'm ignoring the 0 and the 1 for now. I mean, you can write them down if you want to. We're going to plug them in the end, so I don't really care if they're in the process throughout, because this is kind of a messy process with integration by parts for this anyway. So we need to do u times v. That's the part across the top. So I have x times the natural log of 4 plus x squared minus the integral of v du. And you'll notice if I do that piece, I have the 2x times the x, that's 2x squared. And the denominator is 4 plus x squared dx. The first part's fine. I mean, we don't care about that. We don't have to do anything more with it. We'll have to put numbers in it in the end. But this problem right here now has 2x squared over 4 plus x squared. And that's not multiplication. That's division, right? So it's not integration by parts, identifiably that. It's also not U-substitution. Why? Because they have the same exponent value. I can't let the denominator be u and come up with the numerator, because I've got the same exponent in it, and the denominator's exponent, if I take the derivative, will actually decrease. All right, so what do we do? There's one more thing you can do. Long division is the right answer. Again, the reason that this problem is in our question set. We're just going to hit on everything you've ever learned in calculus today. So the division, the denominator rather, is on the outside of the division. The numerator is what goes underneath. That's the 2x squared. All right, so the question you ask yourself as you do long division, if you haven't done it in a little while or thought about it, is what do I have to multiply x squared by to get 2x? 2x squared. Yeah, 2. And then I do it. I multiply 2x squared, or 2 times the x squared, and the 2 times the 4. And then I need to change all my signs. I need to subtract. So of course this adds to 0, which was the goal. And this piece is negative 8. Everybody good so far? So what happened is that 2x squared over x squared plus 4, or 4 plus x squared is how we wrote it before, becomes the 2 that's in the numerator, or on top of the division right here. And then minus the 8, the remainder part, over x squared plus 4, over the divisor. Okay, so I've got my x natural log of 4 plus x squared minus the integral of 2, there's another minus 8 over 4 plus x squared dx. I am happy as a lark to take an antiderivative of 2. That's fantastic. But how do you do the antiderivative of 8 over 4 plus x squared? We could try, but the problem is that if I let the denominator be u, I'm going to get a 2x out of the derivative, and I don't have a 2x in the problem. I only have that 8. We're trying to figure out what the antiderivative of this piece would be. You're going to fall out your chair when you think of it. Nope, it won't help. You can bring the 8 out, still won't help the fact that you've got not natural log, but you're getting closer. Not U-substitution, and it's not integration by parts. Arctangent. Okay, got it. That's right. So I told you you're going to fall off the chair. This is an arctangent form. Told you this problem is going to like do every single thing you've ever learned in calculus, and I'm pretty close, right? I mean, we're pretty close at this point. Yeah, that's arctangent. Okay. Whew. All right, so in arctangent, we have a u and we have an a. I think that's what they used on the notes you've done before. Our u here is just the x. That's no problem. What would a be in this problem? It'll be 2, because it's the square root of the 4. Okay? All right, so some pieces of this we already know because we've already written them down, so let's just rewrite those. I have x natural log of 4 plus x squared. I have the antiderivative of 2, that's 2x. And if I distribute this negative through, I've got the negative 2 and I've got a positive 8x here, so this is then plus the 8, which people said I could factor out, which I totally can. The other piece of this is the arctangent piece. So I'll move this over so I have space. What does the arctangent formula say? You guys have sheets. I didn't have my sheet here with me.
1 over a times the arctangent of
Okay, 1 over a, so that's 1 over 2 times the arctangent of what?
u over a.
U over a, so that's x over 2. And then somewhere in the end I would have a plus c. I'm not going to have a plus c on this problem, though. Why? I have the 1 and the 0 I've still got to deal with. Oh, but we're getting so much closer. We don't have any more integral symbols, right? What happened to my 4?
On the right side, they all have x's, so your last one's going to be minus 0.
All right, so x natural log of 4 plus x squared minus 2x plus 4 arctangent of x over 2. And we're going to evaluate that at 1 and at 0. All right, so if I evaluate at 1, what does that give me? The natural log of 5, right? Minus 2 plus 4 arctangent of 1/2. That's what I get when I plug in the 1. When I plug in the 0, the first two pieces go away because it's 0 times the natural log and it's 2 times 0. So the only thing I have left is going to be possibly the 4 arctangent of 0, which we need to decide if what value that is. So let's see what we do know. Do you know the arctangent of 0? It's 0. Yeah, and your calculator can actually help you on that one. Unit circle, of course, does as well. This piece is 0. Arctangent of 1/2, that's actually not a unit circle value. It's actually not. So we don't have any ability to simplify that, which is good news because that means we don't have to, right? And the natural log of 5 and the 2, those can't be combined or anything. So our answer is actually the natural log of 5 minus 2 plus 4 arctangent of 1/2. That is our answer for this problem. Now, let me just pause for a second. I know we've got like 1 minute left. Think with me on all of these. I know you've got WebAssign, which tells you if you're right or you're wrong. I know that. But let's say, for instance, you think WebAssign is wrong because you were just so sure that you were right. Or let's say you were confirming something on a test or a quiz that you wanted to, or on a written homework assignment or something like that. How could you find out if you did it right? There's 2 ways that I can think of. Take the derivative. That's one way, right? So if you're working a problem that is not a definite integral problem, so everything but this last one, you could take the derivative and see if you get the same thing right back, right? Absolutely. What if you're doing a definite integral problem? How can you confirm your answer? Your calculator. You can take the original first equation and put it in there, and you can use the integral function, right? Put in the 0 and the 1 and see if you get the same decimal approximation. All right, fantastic.